Welcome back, everyone. This is Professor Herring. In this video, we're going to continue learning about gases. Specifically, we're going to learn about effusion and diffusion. We're going to talk about the beginnings of the atmosphere, and we're also going to learn how to recognize graphs that relate between pressure, volume, temperature, and moles. These are the Charles law, Boyle's law, and Avogadro's law. Let's begin. So at the end of the last video, we talked about how if you have a given sample of gas but change its temperature, we're going to get a change in the distribution of the gas particles' speeds. A similar effect can be seen if we keep the temperature constant, but we use different gas particles that are varying in their molar mass. And so in this plot, we're looking at the temperature being constant, but the molar mass changing. And we're using 4 different gases here. And what we see is that at the same temperature, different gases, they have the same kinetic energy overall, but different RMS speeds. Remember how we said that the kinetic energy is going to be proportional to 1/2 mu squared, where this is the mass and this is our speed. And so what we see here is that because they have the same temperature, which is proportional to the average kinetic energy, they have to have, those values have to be the same. In other words, an increase in the molar mass is going to lead to a decrease in the overall speed. And so the summary here is that lighter gases move faster and heavier gases move slower. We saw that when we looked at the simulator and we looked at the helium versus neon that were bouncing around in the container. So let's see if you can practice with this. Shown below are the distributions for 5 gases at the same temperature. What's the approximate RMS speed of argon at this temperature? Well, you might be tempted to go and to solve for the RMS speed using this equation we saw before. We know, since it's argon, we would know the molar mass. We know the R value, but we don't know the temperature. It's not given to you. So what do you need to do here? Well, you need to remember that the mass is going to be inversely related to the speed. And so by looking at the molar masses of these different gases, we can match them with the appropriate curves. So helium is approximately 4 grams per mole. Argon, let me look it up here, is approximately 40. Chlorine is approximately 71. Hydrogen is approximately 2. And methane is approximately 16. So again, because we know that the lighter molecules move faster at the same temperature, the curve that represents the highest RMS speed is going to be hydrogen. The one that has the lowest RMS speed is going to be chlorine, and so on. What we can do then is then approximate the RMS speed of argon, knowing that it is the second slowest, by interpolating and seeing that it is a little bit less than 500 meters per second. We look at our answer choices. The one that best matches that is going to be B. From this, if you wanted, you could then actually calculate the temperature by taking and solving, rearranging this and solving for temperature instead. I'll leave that to you to do if you wish. So when we talk about gases in motion, there's 2 processes that we want to differentiate. One is effusion. This is where you have gas in a container and there's an opening that is just small enough for one particle to go through. Therefore, there's no collisions between the particles as they're passing through, only on either side of the container. And this is in contrast to what's called diffusion. And in diffusion, the gases are that we've got multiple different types of gases and that they are spreading to each other. So you might think of this as a scenario where you're in your house and maybe you're upstairs. This is your bedroom, and your dad is downstairs cooking in the kitchen, and he's frying up some juicy bacon or something, and you can smell the bacon particles throughout the house. As the bacon spreads throughout the house, the gaseous bacon particles, that's because of diffusion. We only get effusion when it comes to a very specific instance of moving from one part of a container to another through a very small hole. And so while this is rare, we can use it to relate the speed to the molar masses and compare those rather easily. And so that's what we're going to do here next. So the rate of effusion, which is going to be approximate to diffusion, is proportional to the RMS speed. When we measure the effusion rates of two different gases under the same conditions, we can express that as a ratio. So because the rate is proportional to the speed, we can set up this relationship. And since the speeds are equal to square root of 3RT over m, we can relate them as follows. But because they're in the same conditions, we're going to be able to eliminate a large portion of the different factors and simplify. Because this was 1 over m1 over 1 over m2, then when that simplifies, it is inverted. And so what we see is that there is an indirect relationship between the ratio of the speeds, or the rates, and the ratio of the molar masses. A scientist by the last name of Graham studied this, and this is what we call Graham's law. And it says what we've seen already, that the light molecules effuse or diffuse faster than heavier molecules. And this is the exact same thing that we saw when looking at the distribution curves. Our light versus heavy. We just have a simple way to actually compare them mathematically. So why don't you try this? If we want to rank the following gases in order of increasing rate of effusion, we're going to use Graham's law. Go ahead and pause the video now to try this on your own before moving on. Welcome back. So again, using Graham's law, we know that the rates of effusion are going to be equal to the ratio of their molar masses, and taking the square root of that. So high molar mass means low rate. So when we take a look at the molar masses of these different substances, oxygen is 32 grams per mole, ammonia is 17 grams per mole, xenon, I have to look up here, is about 131 grams per mole, and chlorine is about 71 grams per mole. So we want them in order of increasing rate. That means we're going from slow to fast. Chlorine is going to be xenon is going to be the slowest because it's the heaviest, followed by chlorine, followed by oxygen, and then finally ammonia. That leaves us with answer choice D. Okay, let's try another problem. An unknown gas effuses at a rate of 1.49 times faster than chlorine. What's the identity of the gas? Pause the video and try this on your own before moving on. Welcome back. So if we're going to use Graham's law here, we know, let's start by defining our different variables here. We'll call gas 1 our unknown gas and gas 2 chlorine. Since we know that the unknown gas effuses 1.49 times faster than chlorine, this is really just 1.49 over 1. The molar mass of chlorine is 70.9 grams per mole, and the mass of the unknown is M1. We first take and square both sides of the equation, rearrange and solve for M1. By doing so, we see that it's equal to 31.9 grams per mole. At that point, we can then add up. This was 131 grams per mole. This is about 44 grams per mole, 17 grams per mole. This is 48, and this is 32 grams per mole. And so this is our most likely molecule. Let's talk about pressure some more. Pressure is caused when molecules collide. It's defined as the force exerted per unit area when molecules crash into some object. Force is measured in newtons, and area is measured in meters squared. And the SI unit for pressure is called the Pascal, and 1 Newton per meter squared is equal to 1 Pascal. And it turns out that there are a variety of different types of units. We have atmospheres, pascals, bars, pounds per square inch, torr, millimeters of mercury. And you might wonder, why do we have so many different units of pressure? Why can't we just stick to one? Well, that's what the atmosphere is trying to do. And the problem is that in different fields, applied fields of chemistry, such as meteorology and engineering and oceanography, and in different cultures, they use different units for historical reasons and for reasons of simplicity based on their applications. So we're not going to focus on converting between the different types of units, although you will need to practice doing that. But you want to be familiar with the idea that different types of professions will use different types of units based on whatever's most convenient for them. And so 1 atmosphere of pressure is defined as the pressure that of the atmosphere felt at sea level. And that's related to pascals and bars and pounds per square inch, torrs and millimeters of mercury. The actual atmospheric pressure is going to vary based on your altitude and the weather. So essentially, we can think of it as, here's the Earth. If we have, a mountain up here, and the atmosphere is up here, the atmosphere, you can think of it as this column of air. And for every square meter, it's exerting this pressure. Well, as we go up in elevation, that total volume that a square meter occupies gets smaller. And I apologize that these are not all equal in length, but you get the idea that at higher elevations, there's smaller total volume of air, and therefore there's a lower total pressure. Weather also plays a role into the actual pressure as well. And if you're interested in learning more about that, then there's some excellent weather classes that you can take at Penn State, or just pick up a good book about the weather. So gases are described, the state of a gas can be described by the number of particles or moles of gas, the pressure that it exerts, the volume that the gas as a whole occupies, and the temperature. And these variables depend on one another. We can, if we look at the relationship between pressure and volume, then we call that Boyle's law. Charles' law looks at the relationship between volume and temperature, and Avogadro's law looks at the relationship between volume and moles. And we're going to take a look at these each in turn. Again, Boyle's law looks at the relationship between pressure and volume. And since they're directly related, what we see, they're indirectly related. As the pressure goes up, the volume goes down. And so that's what we see when you do experiments in the lab. High pressures, here on the upper left-hand corner, lead to lower volumes. higher volumes in the bottom right-hand corner lead to lower pressures. And this is the same regardless really of the temperature at which we're performing these experiments. If you make a plot of pressure versus 1 over volume, then we get a straight line. And that's because we're looking now at the inverse relationship between these two. Charles' law looks at the relationship between volume and temperature. And it is through Charles' law that we actually learn that there is an end point, a lowest temperature that is possible to be reached. We call this absolute zero. If we extrapolate for any given ideal gas, its temperature as a function of the volume, the point at which it reaches zero volume is the same regardless of the gas and regardless of the pressure. And we call that absolute zero. This is where, because it's related, we're relating it to the temperature scale in Kelvin, we see that the value is at negative 273.15 degrees Celsius. That's where the value comes from. If we want to convert from Kelvin, we take the temperature in Celsius and we add 273.15 to it to get the temperature in Kelvin. Finally, looking at Avogadro's law, we see that there's a direct relationship between the number of moles of a gas sample and the volume that that sample occupies. And so the higher number of moles at a given pressure, the higher volume that it occupies. And we see that this trend holds true at a variety of different pressures. Thankfully, however, you don't need to have all of these laws memorized. If we combine them together, we get what's called the ideal gas law. The ideal gas law is going to relate Boyle's, Charles, and Avogadro's laws together through a constant that we call the ideal gas law constant. And you probably saw this when you took high school chemistry. And we're going to go a lot more in depth into this in a future video. But for now, what we want to do is take a look at how these relate and looking at a plot. So if we have a rigid container that has a fixed volume, and we measure the pressure as we are adding gas to the container, we plot the pressure as a function of the gas. If the temperature is constant throughout the process, we want to know which of these variables represents the slope of the line of that plot. Pause the video now and think through this before watching the solution. Welcome back. So how can we think about this? Well, we know that there's a relationship between pressure, volume, moles, and temperature. If we rearrange this to solve for pressure as a function of the moles, then we can see that the slope is simply the other variables, which gives us then that the slope is equal to R times T over V. You could, if we were to make a plot of any of the others, volume is a function of moles, volume is a function of temperature, etc., we could perform a similar analysis where we could solve for the y variable as a function of the x variable and see what the slope would be. That's it for this video. Thanks for watching. If you have questions, ask on Piazza, in office hours, or in recitation. Have a good day.